Hello, my name's Andre, and this is my very first YouTube video that I have ever built. Well, made. This is my redstone testing world, and over the course of the next few videos I will be showing you eventually how to build the basic components to a computer. First things first, you need to know how redstone and logic gates work. This is redstone ore. It's most commonly found in 2x2x2 areas, usually below y equals 30. However, it can be found further up. If mined, it gives you redstone, a random amount, and also experience. From this block here, I'm getting quite a bit of experience, and also a total of 35 redstone. That's good and all, but what does redstone actually do? Redstone is almost like electronics, but for Minecraft. It carries signals, and you can do some fancy things with it. This is a switch. It will light up any redstone dust that's been placed next to it. However, you do have to be careful, as redstone dust only has a certain amount of length that it can go to before running out. As you can see, this redstone dust is powered, but this one isn't. A redstone line that extends the normal 12 block limit can be made quite simply by putting down a repeater. They put it back up to maximum signal strength, however at the slight catch of being slow. These repeaters have a delay on them, which can be changed by lengthening them by right-clicking on them. Each one of these is a tick, so it's currently on 1 tick, 2 ticks, 3 ticks, 4 ticks. Now, 1 tick is approximately 1/10 of a second, as can be shown here. All of these repeaters have been put to 4 ticks, which means that 4 by 6, it should take approximately 24 ticks, or 2.4 seconds, to light up this lamp. Items can also be used. This is a hopper. It allows items to flow from one to another depending on the flow of it. As you can see, this one's flowing into that one, flowing into that one, flowing into that one. However, if we wanted to flow all of them into a dropper, when we place the item in here, they will fill into the dropper. When the dropper is activated by powering it with some sort of redstone device, such as a torch or a lever like this one, it will fire it out. Now, of course, it's not currently on the ground because I have command blocks keeping all items despawned, but you get the idea. These are called observers, and when you place them down, they don't really do anything at first. But by putting a redstone line here, we can see that whenever a block update is in front of it, it puts out a redstone signal. Now, this can be quite handy depending on what you're using it for. It can also detect changes in redstone. Oops, wrong way. It can detect changes in redstone. I will put a redstone lamp down so that you can see this quite clearly. It doesn't just detect when signal is on or off, it also detects changes in signal strength. For example, every time I turn on one of these levers to change the signal strength, that one will power. However, one thing to note with this is that any observers following this repeater will not, because no matter what the signal strength is, with a repeater it's either on or off. Pistons are quite handy. They can move blocks around. And there are two types, sticky pistons and normal pistons. Normal pistons, when powered, just push a block around, and for most purposes, this is fine. However, sticky pistons, given a 1 tick pulse, do the same thing. Of course, 1 tick being 1/10 of a second, as you know. However, if given any other pulse, it will pull in the block. This is quite handy in many situations, such as in this buffer circuit. When I flick this lever, all of these pistons push down their blocks, so that repeaters can't push a signal through the block. However, when you flick the switch again, they retract the blocks, allowing a signal through. This is a nice elegant solution to allowing signals to pass through something, or to stop them from doing so. As you know, a 1 or a 2 tick pulse is enough to cause them to retract their block. However, a 1 tick pulse will cause them to spit it out. In this specific circuit, that's not wanted. However, in some circuits, it can be quite handy. And of course, redstone torches, how could I have forgotten? A redstone torch pretty much just puts out a standard signal strength, but if there is a signal coming in, it will turn off the torch. Now, in digital logic, this is actually called a NOT gate, and you'll come in later. Now for some logic gates. Here is a very basic one, a NOT gate. This is comprised of just a redstone torch, nothing else. As you can see, when the input is off, the output is on. When I flick this, it turns off. It's pretty much the opposite of the input. It is not what the input is. An AND gate, the output is only on if both switches are on. You can see if this one's on, nothing. If this one's on, nothing. But if they're both on, then the light turns on. As you can see, this one works by pushing a block across, as was stated earlier, and allowing an output, because this one is pushing the signal into that block, and you've got yourself an output. This can also be swapped out for a repeater, both work. This is an OR gate. It works if one switch is on, or if the other switch is on. Sorry, that was my Facebook. So this OR gate is pretty much just the two lines leading straight in. Nothing complex, very straightforward, this one. So, NAND. NAND is literally just a NOT AND. It's just an AND gate with a NOT attached. So it's on unless both are off. The complete opposite of the AND. Very straightforward. A NOR gate, again, NOT OR. Same logic. It's just a NOT gate attached to an OR gate. As you can see, same logic, just with the little NOT gate on the end there. This is a different form of AND. It's a little more complicated, but it is smaller and actually works faster. Your input here turns off this torch here, but this line is still powered because of that one, and vice versa. Only when they are both off does this light turn on. And yes, you can make a NAND in the exact same way. You just put a light there. Now if we put an output, as you can see, unless both of them are on, that one's off, unless they're both on. This is an XOR. Now these are big gates, I will not lie. These do get very complicated, and at first glance you probably can't really tell what's going on here. Make it a tad simpler, because this was an old design. So this is an XOR. As you can see, the light there, if both are off, it's off. That's on, but if both are on, it's off. XOR is short for exclusive OR, or a special type of OR gate. It is literally just an OR gate, however if they are both turned on, it turns off the output. Now I won't go into the logic behind this one, because this one is a big gate. But it's fairly straightforward for building, even if the logic behind it is complicated. And of course the XNOR, which is just a not exclusive OR. It's just the exact same thing, just with a NOT gate on the end. So, those are your basic logic gates, and as you can see, unless both are on or both are off, that will be off. So, they are your basic logic gates. Now for something a little more complicated, binary half adders. Now I will be releasing a video later on. I'm not sure if it'll be in a couple of days or a couple of months, I really don't know, but it will teach you how to read binary. But if you already know how to read binary, then good for you. This step won't be as complicated as you think. This is a binary half adder. The idea of this is to add two numbers together in binary. Now you can turn it into a half adder-subtractor, but I'll get round to that afterwards. Now you may recognize this as an XOR gate, and you would be correct. This is in fact an XOR gate. However, this up here is an AND gate. I know I said I wouldn't be going into how it actually works, but you technically need to know. So first things first, as you can see, for that light, it is your standard XOR. However, this light acts as an AND gate. So how does this work? Well, first, I will quickly build one so that you can see. It literally is just this easy. With 2 blocks up on there. So what happens is, when you have your switches down here, flicking one will turn off this torch and hence turn this one on. And hence the output is on. Whoop. Turning this one on will do the same over there. Pretty much meaning if they're both off, the output's off. If one of them's on, it's on. However, these are also powering this. And if one is on, it's still powered. If the other one's on, it's still powered. But if both are on, it activates this torch, which powers these lines and turns off the output, because these are now powered. However, you can actually take the data from, or the signal from this redstone, and it will act as an AND gate. And hence, by putting some redstone there and there, and your torch, you've got yourself an AND gate. As you can probably see. If I put that there, and turn these off, you've got yourself off. Turn that on, it turns that on. If you turn this one on, it turns it on. But if you turn that on, if both are on, it turns that off, and it takes this line into a output. And this is actually your half adder. This is the whole unit right here. This is your half adder. Your output of the XOR would be here, also known as the carry, not the carry. This is called the sum. This is called the carry, because this carries over to the next bit. Again, if you understand binary, it makes more sense. Okay, this is a binary full adder. The half adder is good and all, but it can't take in data from the previous bit. This, however, can, and as you can see, it looks very similar to just two half adders, and it actually is, except you have this line running down the center. This is your carry in, and this is your carry out. The idea is you have two half adders. The carry out of both adders goes into the carry out of the full adder. This is the carry out line. So those were acting as AND gates. These two ORed together. That's what this does. If either one is active, this activates. It comes down here and flows into the next module. This is the carry in line, which you would take from just that of the previous one. I'll show you how to link them in once I've shown you how to build it. Now, the first half adder is very straightforward. It's just your standard half adder with your output. The second half adder takes the output of the first as its input, and the input of the carry in, which was the carry out of the previous module, and it puts it into the second one. And again, the carry out of this is ORed with that, and the sum of both this one and that module there is displayed by these two. Now to show. When one is on, that's on. One is on, again, that's on. But when they're both active, that one's turned on. However, with this, if that is active, it will turn that on. So, this is a full adder. Let's get into it. You want to put down 2 blocks like this. Leave 3 spaces, and then 2 more blocks. Put redstone torches on these sides and on the top here. Redstone like this, and of course that. Then you'll want to build up the rest of the XOR gate. Put a redstone torch there with a dab of redstone on top. Put those the same way. Your redstone torch, redstone on top. Now, put redstone there, there, and there. So the output of these torches, so the output of this thing, is put into here. Then, once you've done that, I'll just put down some levers as the input. Once you've done that, you'll want to put a redstone torch just there, a block, and then a redstone torch with redstone on top. Next, you'll want to put your block of diamond there, or any block, it doesn't really matter. I'm just using diamond because it looks nice. Redstone there, and then flow that down 2 blocks. Your block there, and this is your input from the previous module. That goes into there. This block has to be here, otherwise these two join. So, once you've done that, that's more or less complete. You've got yourself your input, you've got yourself your output for the carry, and you've also got the sum over here. I prefer to keep them just together just to show you. It doesn't have to be a line like that. And as you can see, works like a charm. And when we turn this one on, it activates both. This is an example of a full adder array. You can attach the full adders by taking the carry out of one and putting it into the carry in of the next, sort of like this. So they just nicely flow into one another. And in this case, you would build it up, and that would be the output of the other one. As you can see, it would match up there. Now, as you can see, I have indeed put them all in, but this first one is only a half adder, not a full adder. So what's going on there? Well, the first bit Because it's the very first, there is no module before it, and hence you don't need a full adder on the first bit, you only need a half adder. The rest have to be full adders, but this one's only a half. So, I will put the outputs here, and of course the carry out, and I will add two numbers together. Let's say adding the number 3, 1 plus 2, with the number 5, 1 plus 4. Now in that case, 3 plus 5 is 8. 1, 2, 4, 8. 8 has lit up here. And if we were to string more of these together, we could do even bigger numbers. If we just turn them all on, as you can see, they're all lit except this first one, which, again, because there's no module before it, means that there's no signal coming in to override that. So that is how you would build an adder array. Well, congratulations to you, you've now finished your full adder. But now turning it into a subtractor. You would think that's actually pretty complicated, but it's actually not. It's very straightforward. So, what you'll want to do is get your adder, come out a few blocks, and then build an XOR gate, just like I showed you earlier. We don't need the extra AND gate, however. The torch that would normally be there, we don't need that for now. So we would do that, and then take the output. That is your XOR gate. So now that you've done that, we'll want to take an input. Pull this out a bit, and this one will run up into here. And under normal circumstances, as it is now, the XOR gate, because it has no other side to it, it will act completely normally, just like a normal complicated piece of wire. However, to turn it into a subtractor, we would flick this switch. That would turn it from an adder to a subtractor. So what we'll want to do is build it up and over this wire so that we have a signal flowing through. Now when we flick the switch, eventually all of the adders and subtractors will be connected together. So again, if we do that, we would put one there. Now as you can see, this is skewed a bit. There's nothing I can really do about that. Unless you, hold on, just thinking out loud here. If you do that, I know it's not a very elegant solution. If you do that, yes, that will work. So you'll want to pull this out here and just build up another one of these. Another XOR gate. So, once you've done that, you want to take the output of the XOR and flow it into here. Make sure that, it's suggested that all of them are on the same side. So, say the left side of this is connected to your subtractor adder unit, then you'll want all of them to be like that, the exact same. So, now that you've got that, again, you would pull this all the way through. Pretty much just try to avoid the wiring. And then up. And again, you would repeat. Your adder-subtractor should look like this. You've got your adders that you built earlier, and you've got these. something I forgot to mention is make sure that when you're passing by these, connect this line to one side of this, just one side. As you can see here, this line is connected to this side of it, whereas this side goes out to a switch. And this is continued for all of them. Just make sure in situations like this that you don't have a piece of redstone, because then these will power the block and hence power them. So just be careful of that. In the end, when you flick each of these, each torch should go out individually. Just checking here. Yep. It looks all good. And the last one, yes. And to make sure you haven't got any bridging, when you hit this lever, this light, and this light, the three that are connected to the XOR gate, should all be off. But these should all be on. And everything should flip around if we turn these on. Yep, this is on, that's off, on, off, on, off. That is correct. And that is how you make sure that everything's correct. Now, I would suggest having a single lever over here to make sure that it's adding or subtracting. For example, at the moment it's in adding mode, now it's in subtracting. That's sort of how it works. So yeah, just link this line over and you've eventually got everything fine. Now this is most of it, but there's still one thing left to do. Now to finish off your subtractor, you'll want to put another XOR gate on each of these outputs. Ignore this one. For some reason this one's perfectly fine, but these you'll want to put XOR gates on. So, once again, build up the XOR gates, just like you have before. So, you've got yourself your torches, your redstone, and so forth. I'll finish building these. I will see you in a moment. Okay, now that you've successfully built your OR gates, mine were a little too close so I had to push them forwards. Now that you've built your OR gates, you want to connect the inputs that are left over. You want to connect them to your line that dictates whether you're adding or subtracting. So, in this case, I will just pull this over here and move this line up. This is where repeaters come in handy when you have lines that are this long. So, down it goes, and we'll make it go all the way over. I'd suggest putting a repeater as close as you possibly can, so that then there's no discrepancies between the timings of each of these units. So you've got yourself a line that's going into there, and so forth. I'll see you in just a moment. Now that you've finished linking these up, you are just about done. So you've got your outputs. In my case it's 3 sums and the carry left over from this one. I just pulled it forward so that it was easier to see. And of course you've got your Add-Subtract button. So let's try this one last time. So we are adding the numbers 3 and 5 to give us 8. There we go. However, if we wanted to subtract, we flick that, and we've got the number, we'll go the number 5 minus the number 3. We should be left with 2. And there we are. So that is your adder and subtractor completely finished. This is your first step this is your first step into building yourself a full-on computer. Now, you can compress these, you can make them smaller if you want. This is just to show you, so I kept everything spaced out. So you've got your XOR gates for determining whether you're adding or subtracting relative to that switch. You have your actual adders, which of course work backwards if you're subtracting. And you've got your XOR gates, which pretty much say that if you are subtracting the value, reverse them. And again, you don't need an XOR gate on this last one, the carry out. So, thank you for watching this video. If you liked it, please make sure to leave a like. And yeah, if you want to subscribe. And I will be putting out a video shortly on how to read binary, and then eventually onto some of the other wonders of how to build a computer. Eventually even getting into that big thing, which is multiplication. Adding, subtracting, multiplication, and eventually division, which I have yet to work out. But yes, once I've done that, computers ahoy. So, if you liked it, leave the like, and yeah, I will see you later.